Hello everyone, we are group 4 and this is the outline today. First, we're going to introduce 1-2-3-4-5, which is a technique for converting a single image into a detailed 360-degree 3D texture mesh. And the other model used in our project is TransMVSNet, which is a multi-view stereo transformer model. 1-2-3-4-5 is a method for single image for multi-view 3D reconstruction. It utilizes 0-1-2-3 and SDF-based neural surface reconstruction. And 0-1-2-3 is a view condition 2D diffusion model, which takes a single image as input and generates multiple views of the object. And SDF-based neural surface reconstruction is a reconstruction module which takes multiple source images with corresponding camera pose as input and generates a textured mesh in a single feed-forward pass. This is the pipeline of 1-2-3-4-5. It consists of three primary components. The first is a multi-view synthesis. Here, it used a view condition 2D diffusion model 0-1-2-3 to generate multi-view images in a two-stage manner. The second is pose estimation. It estimates the elevation angle theta of the input image based on four nearby views generated by 0-1-2-3, and then obtain the poses of multi-view images by combining the specified relative poses with the estimated pose of the input views. And the third part is 3D reconstruction. We feed the multi-view posed images to an SDF-based generalizable neural surface reconstruction module for 360-degree mesh reconstruction. And the process begins with 0-1-2-3, a view condition 2D diffusion model, which takes a single image as input and generates multiple views of the objects. 0-1-2-3 assumes that the object is centered at the origin of the coordinate system and uses a spherical camera, which means that the camera is placed on the sphere's surface and always look at the origin. For two camera poses, x1 and x2, here we use theta as polar angle and phi as azimuth angle, and r is the radius. And x1 and x2 are two images of an object captured from different views. The model and the relative camera transformation is like here. And the model of 0-1-2-3 aims to learn that we input the relative camera transformation to the model, and it will predict the synthesized views that is similar to x2. And the reconstruction method of 1-2-3-4-5 takes multiple source images with corresponding camera pose as input and generates a textured mesh in a single feed-forward pass. The step of the module is first extracting M2D features maps using a 2D feature network. And second, construct a 3D cost volume whose contents are computed by first projecting each 3D voxel to M2D feature planes, and then fetching the variance of the features across the M projected 2D locations. And the third step is compute the cost volume by using a sparse 3D CNN to obtain a geometry volume that encodes the underlying geometry of the input shape. The fourth is to predict the SDF at an arbitrary 3D point using MLP that takes the geometry encoding volume as the input. And the last step is to predict the color of the 3D points using MLP with geometry encoding volume, view direction, and 2D features as input. And the two-stage source view selection is as follows. First, rendering n ground truth RGB and depth image. And second, use 0, 1, 2, 3 to predict 4 nearby views for each of the n views. And third, feed all 4 times n prediction with ground truth poses into the reconstruction module, and randomly choose one of the n ground truth RGB images views as the target view. The view selection strategy is crucial because uniformly choosing source views from the sphere surface would result in larger distance between camera poses. A two-stage source view selection addresses this issue, as cost-volume-based methods typically rely on very close source views to find local correspondence. This is why the two-stage source view selection is important. The second model used in our project is TransMVSNet, which is a multi-view stereo model with a powerful feature-matching transformer to leverage intra and inter-attention to aggregate long-range context information within and across images. To better adapt FMT into an end-to-end MVS pipeline, we introduce an ARF module to adaptively adjust the receptive fields of convolved features. And this is the pipeline of TransMVSNet. It consists of 4 primary components. The first, FPN, is to extract image feature of the input views. The second part is ARF. It bridges different stages, features, and gradients across different scales. And the third part is feature matching transformer, which aggregates long-range context information within and across images using intra-attention and inter-attention. And the last part is correlation volume generation, which use pixel-wise feature correlation to generate the coarse-to-fine correlation volumes. TransMVSNet extracts basic feature by FPN and introduces ARF modules to ensure the transit from FPN to the transformer. In the feature matching transformer, intra-attention is performed to aggregate global context within images, and inter-attention helps feature searching and matching across images. A transformed feature pathway is connected to pass low resolution features to higher resolution and enable backpropagating gradients of all scales to go through FMT. We then apply pixel-wise feature correlation to generate the correlation volumes, which are regularized with a coarse-to-fine pattern. And the novelty of this paper is that it uses an adaptive receptive field ARF here, and why we need to bridge the gap between different scales feature map. That is because transformer implicitly encodes global context information into feature maps via positional encoding. On the contrary, FPN mainly focuses on the context within a relative local neighborhood. Hence, we introduce the ARF module to bridge the gap between these two modules in terms of context ranges. The ARF module is implemented by deformable convolution, which learns extra offset for sampling position and is able to adaptively enlarge the receptive fields according to the local context. And the dataset we use for 1-2-3-4-5 is Objectverse. It contains 46,000 of 3D models in 1,156 categories. Here we use the pre-trained weight 1-2-3-4-5, 0-1-2-3, and SAM segment anything for background removal, provided by the 1-2-3-4-5 GitHub repository. And for TransMVSNet, we use DTU dataset to train its model. And the DTU dataset is captured under well-controlled laboratory conditions with a fixed camera trajectory and contains 128 scans with 49 views under 7 different lighting conditions. Here we use the pre-trained weights provided by the TransMVSNet at its GitHub repository. As 1, 2, 3, 4, 5, the multi-view images are used to generate 3D mesh by SDF-based methods. We are curious about if it can used for generate 3D point clouds. So our goal is to figure out whether the 360 degrees multi-view images generated by view condition 2 diffusion models will help the 3D reconstruction tasks or not, especially 3D point cloud. In the 1, 2, 3, 4, 5, it generates only 4 different viewpoints at different elevations in stage 1. Then in stage 2, it generates 4 different camera poses for each image from stage 1 here. In our experiment, we generate 8 different viewpoints in stage 1, hoping to achieve more consistent reconstruction. For 1, 2, 3, 4, 5, we use the pre-trained model download from Hugging Face, and for TransMVSNet, we use the pre-trained model provided by the author. Here's our results and analysis. Our model can generate 64 multi-view images from different viewpoints and elevation. Thanks to the powerful pre-trained 0123 model, we can observe that in the images from different viewpoints, both lighting and shape consistency are taken into account in successful cases. In addition to these successful examples, there are many more instances of failed generation. The model generates many misunderstood shapes from the input image, which may lead to the Janus problem in 3D reconstruction. Especially for irregular shaped objects, they will generate repeated shapes in some viewpoints. The model fails to, and here is the point cloud generated by TransMVSNet. The model fails to generate a point cloud in the most consistent multi-view stereo images from 1, 2, 3, 4, 5. Despite the 360-degree viewpoints, it still has many mismatched points in those images, resulting in very poor results in our experiments. Regarding our poor results, we can discuss the following issues. First, generated images. As observed in the cases with highest geometry consistency above, the model still generates a poor point cloud. A possible reason is that TransMVSNet reconstructs the point cloud using depth map estimation. However, in the image generated by our model, almost all backgrounds are white, which leads to significant ambiguity in depth calculation. And the upper row is the depth map by the original DTU dataset, and the bottom row is the depth map that generated from our 1, 2, 3, 4, 5. And the second analysis is that the less common objects in daily life or items that are infrequently present in the dataset can cause the 1, 2, 3, 4, 5 to generate incorrect multi-view images. It fails to generate the correct shape and cause a severe distortion. For instance, we try to generate the A100 GPU, but for some elevations, it becomes generating a black square out of its original contour. And the right image here was a saw, and it generates a very, very strange shape. And the last part is our conclusion. We propose using 1, 2, 3, 4, 5 for novel view synthesis and TransMVSNet for 3D reconstruction to obtain a 3D point cloud. The main effort in our work is to seamlessly integrate the output of 1, 2, 3, 4, 5 into TransMVSNet by ensuring a consistent data format. Additionally, we prepare necessary files such as camera extrinsics and the top 10 view selection matching pairs for each view. We have encountered several technical difficulties in our progress, such as setting up rootless Docker, using containers, implementing model parallelism, and compiling a package with the required C version of OpenCV. The main challenge has been tracing and understanding large amounts of code across different projects. Unfortunately, the results of our concept did not perform well. This may be due to two reasons. The first, additional new views generation in 1-2-3-4-5. We double the azimuth spacing while maintaining the same elevation strategy to generate additional new views. This approach achieves twice the number of output views without restraining the model, resulting in greater overlap between views compared to the original setup. However, since 1-2-3-4-5 lacks multi-view consistency regularization, this can lead to repeated shapes in different views or even Janus problem. The second is camera extrinsics and view selection pair provided to TransMVSNet. We observe that the fourth column of our camera extrinsics, which refers to the translation vector, is significantly smaller than the translation vectors in the original TransMVSNet training set. This discrepancy suggests that the inference and training stages were conducted in different environmental setups for collecting novel views. This gap between the two datasets have led to poor performance in our experiments. In our future work, we plan to enhance the quality of the generated novel views by adjusting the azimuth selection strategy. Additionally, we aim to modify the 1-2-3-4-5 model to generate images with camera extrinsics that more closely match those in a TransMVSNet training set. These adjustments should help us achieve better results. This is our presentation. Thank you for listening.